Can you hear me, Andy?
Yes, doctor.
Yes. Okay. You started recording already?
Yes.
Okay. So we're going to continue with this. If I can find where is my sharing. Oh, it's been shared already. It's not what I want. Let me stop sharing and go back to. Can you see my full screen or not?
Yes, full screen.
Yes. Okay. Okay, so all of these people, this you're here, it's for me, it has a lot of okay. Why? Because this means that when you calculated the inertia, or when you deduced the formula for the inertia in this problem, what we did was we considered normal stresses, right? And you integrated these normal stresses multiplied by the little area, differential area, and multiplied by the position, the vertical position. And you make that equal to the bending moment. Okay? And then we introduce the kinematic assumption, and from all of that, we deduce, okay, the integral y squared dA was inertia. But we started considering normal stresses in the x direction, normal stresses in the x direction, not in the y direction. That's why we only have to consider longitudinal elements, not transverse elements, okay? And finally, this comment here that I mentioned before is that when we work with this type of things, this is we have to keep that this is a large ship problem, okay? Ship problem. When we have to calculate these things for a 20, 30, 40 meter long ship, the results are going to be very small, okay? I don't know if we will have time. I can show you some results, for example, for a fishing vessel, 40 meter long fishing vessel. And the results were that the primary stresses were about 15, 20% of the maximum, the allowable values. Very small. Okay, but in general, it's a good idea to know these things, okay? Now, let's go on. Now, for example, this, as you can see here, this is some calculations that I had to develop a couple of years ago. This is a 112 meter long tanker. In this case, yeah, we have to worry about these things, okay? You see here, this is the distribution of the elements in this section, okay? You have this in your class notes, okay? You see that here I have a double bottom and double side. Of course, there's no need to include double hull in the deck, but yeah. So this is the side girder, okay? So this distance cannot be more than 2.5 meters. So this is 2.5, that's about 5. And it's 8.6. I don't know how much this is, but that's the general rule that we have to follow. You see that this is elements that are very small, okay? And that means that this is a longitudinal framed system, okay? And we have to calculate all of these, to include all of these to calculate inertia. Okay. I'm not going to show the details, but this is the summary. Okay, this is for a frame, which is about here. But we have to calculate the distribution of the inertia along the length of the ship. Okay, so in this area, we have very large value. In this area here, what happens is that we have a longitudinal, not longitudinal, in the forward end, we have some, the ship was like that. And in the forward end, we have something like this. So about this area, okay, so the depth, the height of the beam, whole beam, was much larger than the height at the midship. That's why we had this little increment, okay, in this, about 20 meters from the forward perpendicular, okay? But in general, this is a typical distribution of inertia, okay? And then we see here in the lower part, I'm showing you the sectional modulus, right? And since you see here that we have double bottom, and usually the bottom thickness is higher than the thickness at the deck, because here you have the pressure, okay? The hydrodynamic pressure here. Here, yeah, you could have loading, but in general, for example, in a tanker, there's not much load on here. There's some tubing and all of that, piping, but here we have a lot of pressure. So usually we have these elements stronger than in the deck. That means that in general, the position of the neutral axis, as you can see it here, it's about from the mean depth below. So if that's so, that means that the largest distance from the neutral axis will be to the deck. And this is shown here. This is the red. The red shows the section modulus at the deck, which is smaller, lower than the section modulus at the bottom. Right? These are typical units that we employ in order to express that. Meters, square centimeters. Okay? For the inertia, we use this meter square, centimeter square. Okay? If we use meter to the fourth, usually that gives us very small numbers, right? So yeah, this is typical. Okay, so it's very common. Okay, this is the position from the baseline to the deck. I'm sorry, from the neutral axis to the deck and to the bottom. And this is the most important region as far as the bending moment is concerned. And we see that the distance to the deck is higher than the distance to the bottom. And this is reflected in these results. Okay, so in general, only primary stresses in the deck are expected to be higher. Just considering this primary, because the distances are larger. Okay, these are typical values. These are real values from a ship that operates in our waters. Okay, now this is I warned you about this thing, and finally it came. Okay, in chapter 2, or in chapter 1, we had a sign convention for the bending moment and shear forces, right? Well, in this case, this is a beam, is a whole beam, and Classification Society, for some reason, they decided that they prefer a different sign convention. And this is the sign convention that we need to consider when we do these whole calculations. Okay, so in the upper figure, that's a sign convention for the shear force. In the lower, that's for the bending moment. Which one coincides with our sign convention in chapter 1? Can you identify which one coincides?
The shear force.
The shear force coincides, yes. On the contrary, the bending moment is the opposite. Okay, so I know it will take a couple of days to get used to it, but that's we need to to work like this. Okay, so we have to express the results from the Hall bending using this sign convention. Okay, people? Now, we have to worry because if we have to use this sign convention, then the equilibrium equations will change a little bit. Okay? So if we have loading like this is P of X. Okay, in this case, the partial of Q with respect to X is going to be minus P of X, because this is the same as before. But this is different. So we can say that dmy with respect to X is going to be plus Q. Okay, because there was a change in direction. Okay, people? Are you with me, people? Everybody with me?
Doctor, you put dmy because the direction.
Because in
of the
general, this is a 3D problem. Okay, so we need to start seeing this as this is X, this is Z. So Y is it's X in the forward, Y in the beam direction, and Z is vertical. So Q should be the shear force in the vertical direction, in the Z direction. The bending moment for us, in the case of the Hall beam, it's in the Y direction. That's in the beam direction. Are you with me? People? Okay. So I didn't do this, okay? I just have to follow the rules, okay? So when you do calculations, yes, you have to worry. I mean, you present results for a classification society. This is the sign convention that they employ. So when you mention that the bending moment is positive, that's what they understand, that the Hall is like this. And that will receive a special name in a few seconds. Yes?
Doctor, when we think in the boundary condition on dmy, we have to change the sign?
No, because, yeah, if you had a concentrated force, yes, but in general, in the case of the Hall, we have the shear force and bending moment at 0 in both ends. Because these are free ends. Talk about that in a second. Okay, but that's something that we should have in mind. Okay, the shear force coincides, the bending moment is the opposite. Shear force coincides, bending moment the opposite. One more time. Shear force coincides, bending moment is the opposite. Thus, we have to start getting close to what the profession does, applies. And this is what they do. I'm sorry, we have to follow. That's all. Unless we have to generate a new classification society and we go back to our sign convention. But now nobody will follow us. So we have to follow the gringos. That's it. Okay, so the loading, the P of X. The loading, I mentioned this before, we have 3 components. Weight, That's a big problem we have, because in the ship you can see that there's a lot of weight items, right? So it's a big mess. The inertial response. With inertial response, we mean acceleration, mass times acceleration, right? Because the dynamic pressure generates a lack of equilibrium with respect to the weight. That means that if they are not equal, the system will accelerate. Okay, so in a few seconds, I will mention that. Okay, and then we have static and dynamic pressure. So the three should be combined in order to produce P of X. Okay, so these three, if you want, these three, okay, will produce a P of X. People, right now, primary is a 1D problem. It's a the dependence is only on X. Okay, that's why I insist. You see that the derivatives are total, and clearly I'm setting up that the dependence on P is only on X, because this is a beam assumption. Okay, now and usually consider two situations. Okay, still water and waves. Okay, so still water now means that the ship is floating, it's moving, could move with velocity, but there are no waves. So the free surface or the sea surface is completely horizontal. Okay, and then what we do is we usually consider the contribution from the waves in a very simplified way, since this is a very primary course. Okay, so usually we can differentiate this. Usually we say SW and W. SW, still water. The other, just W means waves. Okay. Now, we need to calculate the response. We need to calculate these loads, right? And it's a very delicate thing. We of course, we don't have the time for that. A little bit of that we do in ship dynamics. That's next year. Okay, but it's a very delicate thing to do. Okay, there are usually three ways to do this calculation. We're going to use two, which are kind of simple, but at least we should know which one are these. Okay, the first one is just to do a full dynamic analysis. So we have a ship, we impose waves, and we calculate the response. So the ship accelerates like this and accelerates rotational. And according to that response, we can do an analysis at different cuts, at different sections along the length of the ship, and we can calculate the shear force, bending moment, torsional moment if you want, dynamic. So all of these will be dependent on time. That's a very complex situation. Okay, of course, we don't have the time to do that. Some of that will be faced in ship dynamics. Some, not much, some. What are the options? The other option is this. Okay, let's suppose that we have a quasi-static equivalent problem. Okay, so let's suppose that, for example, the ship oscillates, and when we do something like this, right, it bends like that, you see that it is this curvature. That situation, it's more or less generated by the presence of the crest in this area, right, that generates this type of bending. Right? And it's what we call hogging. In a second, I will show with another figure. But this is another point during this behavior in which I have two crests, one here and one here in the ship. So if I have a crest here and here, the ship will do something like that. And it will smile. That's what we call sagging, okay? Those are kind of extreme situations. And what we have come out with is that the values of the bending moment and the shear forces, those are the parameters we need to calculate, because with the bending moment, as we show in the first formula, we can calculate normal stress. What we're saying is that we can approximate what happened in the dynamic response. We can approximate that with this situation and with that situation, with hugging or sagging situation. How do we calculate? We assume they are like freeze in a wave. And we accept that this condition is adequate to only estimate the real response. Okay, we're going to take that as part of our calculations. So what we're going to do is we're going to get our ship, we're going to pose a wave, and we're going to try to set, since it is a quasi-static equilibrium, we can have the buoyant force and the weight force cancel each other. And the buoyant force is supposed to represent the dynamic and the inertial effects. That's the general assumption. And finally, we could find some formulation from ship classification societies directly. You can go in the classification society rules, and you will see in the chapter on longitudinal strength. Let me write it here. So if somebody wants to, longitudinal strength. And they will give you formula, for example, for the bending moment in waves, and they will tell you for hugging or sagging, this is the bending moment distribution. So you have to apply formula, and you obtain a value for the bending moment in the midship area. And then they will tell you the distribution that more or less will support. Okay, so they will give you, the distribution is more or less, let me see if I can go here. The distribution, it would be something like, if this is X, the distribution will be something like this. And there will be values for bending moment in still water and also bending moment in waves. And the bending moment in waves will depend if you want in hugging or sagging condition. And this hugging and sagging, they correspond to these situations. Okay, that's method 2. We're going to insist mostly on 2 and 3, of course. No, not 1, because it's a very complex procedure. Okay. So let's say a little bit more about this quasi-static method to calculate the shear force and bending moment in the case of the shipping waves. Okay, now this figure shows the exact situation. You have the ship. Let's suppose that we receive waves from the bow, from forward end. In that case, you will have the largest response in the vertical plane. So you will have a response in the vertical direction. That's what we call heave. You will be oscillating like that. That's what we call pitch. Okay. And of course, once you do that, the structure will bend a lot. That's what we need to estimate. That's what we need to do. Exact. But the problem is that it's very complex. What can we do? What we can do is this. We can assume that these values, positive and negative, can be approximated with the ship considered in static equilibrium. If you have a static equilibrium, that means that the forces that are applied in each condition cancel each other. So the summation of those forces is equal to 0. And they have to be aligned, so also summation of moment can produce a value of 0. Okay? In the upper one, we have what we call the sagging condition. It's always a good idea that you know the translation to Spanish. Okay, so sagging is what we call arrufo. Okay, and hogging is what we call quebranto. Quebranto. People, sagging is bending moment is positive or negative according to the Ship Classification Society's sign convention. Mr. Villalba, what do you say, Mr. Villalba? Mr. Villalba, Arrufo would have positive bending moment or negative bending moment?
Positive bending moment.
Positive bending moment. What do you say, Ms. Valdez?
Negative.
It's negative. Remember, it's the opposite than the sign convention in our chapter 1. So even though it is smiling, according to the sign convention of the classifications rules, this bending moment is going to be negative. Yeah, that's all. Okay. Now we have to practice in order to change our gear. But eventually we will get it. That's why I need to insist on this, okay? Because it may cause problems if we do not do that. Hogging, we have the crest in the central part, so we do that. For example, this one here, is this hogging or sagging that caused this breaking? Ms. Avilés, what do you say? Hogging or sagging? Ms. Avilés, please. Ms. Avilés, are you there? No? Avilés is not here. Andy. Ms. Arechua, are you here?
Good morning, doctor.
In this figure, do you think the ship is in hogging or sagging, which caused the breakage of the hull? This is naval engineering.
In a saggish.
In a sagging?
Hogging.
I have two opinions. What do you say, Ms. Flores? Hogging or sagging? The crest, if you see, you have the crest, right? We have the crest about here. And you see that there is some throw on here. So we have the crest in the central part of the ship. So it's basically hogging. Okay, yeah. So it could be, but as first sight, we consider that's hogging. Okay. I put it this. It's always a good idea to know these terms in Spanish too. Okay. So it's arrufo and quebranto. Okay. Any questions about this? Okay. So people. We have basically three actions: weight, pressure, which is static and dynamic, and inertial effects. Okay, these two will be summarized with this equivalent wave. Okay, now this wave, you see here that the length of the wave, it's about, okay, the length of the wave. You see, this is a W wave. The length of the wave is about the water length of the ship. Okay, so more or less, we have the length of this wave. You see, this is a crest, this is a crest. So the distance from crest to crest is what we call a wavelength. Okay? Now, another thing, of course, is very important is to know the amplitude. Okay? The amplitude of this equivalent wave. Remember, this wave tries to summarize pressure or buoyancy and also the inertial effects. Okay, now to determine this, there were a lot of studies you can imagine. And here, this figure you have in your class notes is taken from P&A. In the numerator, in the x-axis, we have the ship length in feet, be careful. And we have here some formulations. Okay, this is specifically for this condition. Okay. This is the Froude number. I'm sorry, the block coefficient, Froude number, and this is the velocity ratio. This is velocity divided by the square root of length. Velocity in knots and length in Froude number. Remember, it's non-dimensional. So that's that. Okay, and here they have calculated or summarized for different ship length, they have deduced the specific wave height. People, we have to be careful. Okay, oceanographers, they prefer to work with height. Okay, so let me draw here. This is like a wave, right? Okay. So from here to here, this is the length of the wave. Sometimes we call it lambda. There. And this is what we call zeta 0. This is the amplitude, okay? And from here to here, it's also zeta 0. So from here to here, that's twice amplitude. This is what we call the wave height. Okay, so wave height is twice the amplitude. So here in the figure on the left-hand side, lower left-hand side, we have, this is the wave height. This is the effective. So this is the height for this wave, which effectively produces something similar to this result. Okay, and we have some formulations. We can see here that this is a long term. That means that they calculated the dynamic response. They considered irregular random waves. So this is a very nice calculation there. For long term, okay, so they determined that there was the, for example, the maximum a bending moment that you will have in 20, 25 years of that the ship is working in the North Atlantic, okay? Because that's the idea. And if you work in 25 years, you will be able to support all of these bending moments, okay? Okay, now, there are some formulations here. This is very classical, L/20, but you see that for small ships, that produces wave height smaller than the correct ones. For larger ships, that produces much large wave height. And then we have this one, which is one of the most well employed, is the 1.1 square root of the length. Okay, this is one of the most common employed. 1.1 square root of the length. Well, we have to be careful because in this case, this is remember, this is a formulation from the US. Okay, so we have to be careful because the effective wave that we're going to be using is 1.1 square root of length. But this is feet, and this is also feet. Okay, so if I give you, for example, a 60-meter long ship, you have to convert 60 to meters, to feet. Okay, with those values, plug it into a formula, 1.1 square root, and the result, you know that it is feet. So you have to divide by 3 point something, and you get back to 2 meters. Okay, and you have to be careful because remember, this is height divided by 2, and that will give you your amplitude. Okay, now once you have that, you're ready to pose your wave with the same length as the ship length and the height, which was calculated with this approximate formulation. Any questions, people, so far? Any questions? No? Okay. Now, when we work a ship, you receive a couple of examples from Ms. Sayo last week, I think. The draft along the length of the ship could be expressed like this. A mean average or a mean value, you know, if you say mean draft, that means the draft at the midship section. And plus, you could have some trim, right? That's this angle alpha times the position along the length of the ship. Usually we put the origin of the axis at midship. Okay, that's typical of the classification societies. Okay, we put the origin of the reference system at midship section. Okay, so in still water, that's but when we have the draft of the ship in waves, okay, like in this case, okay, like in this case, you see that here, this is T of X. Okay, now here, this is X, and this is midship section. Okay, so this T of X or this T of X could be calculated using this formula. Okay, how is the draft that you have at the still water, and then you can add the profile of the wave. Okay, now in general, this value is not equal to that value. Okay, because when you have a wave, okay, this part here is not the same as this one here, or this part here is not the same as this one here. Okay, so when you do these calculations, you have to iterate in order to find the mean and the mean draft and the trim. In the examples that we develop in class, usually we are not, we don't have the time to consider a real ship. So we use simplifications. For example, we use box barges or something like that, right? In that case, yes, these things can be much easier. But in general, once you superimpose a wave, okay, the mean draft changes a little bit. That's because for example, if you have a sagging condition, you have a crest on the forward end and a crest on the aft end. Okay, these two, the increment in buoyancy in these two ends is not the same. Usually on the aft part is much wider, usually. So that means that if you go up in the surface, this is going to increase this one. So there's going to be a change in small change in mean draft and also in trim that we have to calculate. Okay. Now I put plus and negative because that depends on the condition. Okay. In this case, for example, in sagging, you see that we have a throw in the midship section. So in this case, we have to subtract. So we use the negative sign. And in here, we add, because I have a crest in midship. In that case, I have to use the positive sign, okay? Z0, it's the wave amplitude, and that's that. Here, I have a K times X, right? And K is equal to what we call the wave number is equal to 2 pi divided by lambda. And as we said here, lambda is the wave length, okay? Wavelength is taken as the ship length, equal to the ship length. That everybody has, I mean, it's very standard procedure that we use the wavelength equal to the ship length, because that produces the largest structural response from the ship, okay? And the amplitude, Z0, okay, is calculated after we calculate the effective height of the wave. Remember, this formulation, since it's from Gringolandia, was used using English system of units. And then you have to make the conversion. This is not an analytic deduction. Okay, so here you have to use length in feet, and that's it. Square root multiplied by 1.1, and the result is feet. That's it. Okay. Don't ask me about the 1.1. What are the units of 1.1? No, this is an empirical relation. Questions about these people so far? Any questions about this? Okay. Now, the weight distribution, you tell me. You have this much of this much of that, the whole weight's this, and etc. Pressure or buoyancy and inertial effects. That's why we use the effective wave, if you want. Equivalent wave would be better, right? Now, after we have these two, we're supposed to have them in equilibrium. And that's what we're seeing here. Okay, so to have equilibrium, we have two forces. This is delta, but remember that it's the delta which represents all of these effects, right? And but since we have a static equilibrium, this effect has to be a value equal to that one, and its line of action has to be aligned with the weight line of action. Okay, that's what we need to do, including the profile of the wave, including the profile of the wave. Now, this is something that we already reviewed. Buoyancy, that's force per unit length, is equal to gamma times the area of the section. Okay, and the area of the section depends on the draft. Now, to have this in equilibrium, we have to solve these two equations. We have to integrate this in considering the wave profile, right? So in this case, for example, the draft is lower than the draft at still water. And in this area, the draft is going to increase with respect to the one at still water. And you integrate all of these, and you are supposed to have a result equal to the W. Similarly, for the first moment. Okay, so if we satisfy this, that means that the LCB is going. This is the result of this is going to give you LCB times displacement. So if the displacement is equal to W, then that means that the LCG is equal to LCP. That means that the two are to the same distance from the origin. Okay, so we have to satisfy that. Now, In order to find this, we will do an example. Well, you did an example with Miss Sayo, okay? So you found mean draft and trim angle, right? So that's already been done. And after you do that, we can proceed, okay? And we can make cuts following what we call the section method, chapter 1, okay? So after we assume that everything is in equilibrium, we can go on. If we say that the ship is in equilibrium with a wave, equivalent wave, effective wave, that means that any piece that we consider has to be also in equilibrium. This is the figure that I'm showing here, okay? So if I take this cut from here to here, okay, this is an equilibrium. But in this case, we have to consider both. Remember, this is a negative phase. Negative phase. So this is shear force, downwards, positive. This is bending moment. In this direction is positive according to the Classification Society convention. Remember, SAT, opposite to the one that we use. Okay, so dv dx is equal to minus p of x. P of x, what do we include? We include weight and buoyancy. Weight downwards, with this negative, give us positive. Buoyancy is positive, but it's negative, give you negative. Then we integrate this. Integrate from here to here. But at the end, the shear force is 0. So that's what we integrate. Oh man, I'm sorry. This figure is a little bit odd, but we're integrating from the left end, from here until here. But on the left end, on x equal minus 2, that's 0. And the result is give us the shear force here. What we can do, since we are going to use this figure, it has to be equal to the integration from x to plus L over 2. Okay, has to be the same. Yeah, people, any questions about this? Now, in this case, since I can integrate from here till the end, of course, it looks like the integration will be shorter than if we integrate from this all the way up to here. Am I clear, people? Okay, if I integrate from here till here, that's what I'm expressing here. But I could also get the same result starting here and go up to here. Okay. And similarly, for the bending moment, okay, I could do the same. But here, remember that I have the negative sign. Here, I don't have it. We have to be careful. That's because the sign convention employed by the Ship Classification Society. It's not my fault. It's theirs. Okay? And we can integrate, again, from minus L over 2 up to here. We can obtain this. If we do this, we could obtain the same result. So we can integrate from here to here. Remember that if we integrate from here until here, we're going to have the same. I'm missing something here.
Minus.
A minus, yes, a minus. There you go. Thank you. Thank you. Yeah, thank you. So if this is equal, that means that I can take this to the left-hand side, and the combination of the two would be equal to 0. And if you combine from minus L over 2 to x, and from x to L over 2, this is equal to this. Because the integration of b is w. Integration of b of x is this. Okay. I don't know, use this sub-index here. People, how were the results from the experiment? People, did you get the result from the experiments? Anybody did you get result from the experiments? How good were the results from the experiment? I didn't have the time to check them.
In my case, I checked an easy plot, the graphics, and I have a great approximation. I think I have continuously lines for each weight when we move.
But did you calculate Andy, did you share with them the weight of the tube? So you have the weight of the tube, the weight concentrated at the center, and the weight at the ends. The weight at the ends, you have to move it, and according to that, the shear force at the connection would change. But you have two load cells, and basically you have to add the two values, because the combined two will give you the shear force at that cut. Go on, Andy.
No, I didn't share the way of the tube.
Yeah, you have to do that. And when is this due? When do you have to turn this result? This report. Andy, do you remember?
No, I don't know.
Okay, I have to check it out. Okay, people, please keep this report going, because I would like to see these results. I'm going to post some work to be completed individually about this primary behavior of the ship hull. Okay, so it's 9:03. I'm sorry to get too late. Have a good day.